Hello. All right, I'm going to talk about this guy again here. Please remember what we did the other day. We talked about him rolling downhill without slipping, and we got the velocity at the bottom of the hill in terms of just G's, H's, R's, M's, thetas, whatever they allowed us to use expressions for. But anyway, that ended up being 4/3 GH was what that expression was, okay? And what I'm going to now talk about is how to do a very similar thing, but using energy, all right? So, again, the reason why I drew the face on there is so you can tell if this item is sliding or if it is rolling, okay? Please realize if this dude is sliding, then he has kinetic energy, right? Anything that moves has kinetic energy. In this example, if it's just sliding, then he has linear kinetic energy, right? And it would be true, it's probably easier to visualize just that if he's sliding down or sliding up, it doesn't matter. There is linear kinetic energy, which you all know it's 1/2 mv squared. That's easy. But please realize if this guy's rolling downhill, well then gosh, there is not only linear kinetic energy because his center is moving in a straight line, you know that, but all the other pieces that this item is made of are going in cycles. So they have rotational kinetic energy. So if it's rolling, it has both linear and rotational kinetic energy. If this guy were just attached to some sort of item that was making him spin, say just like this, but not rolling, just rotating or just spinning, then he would only have rotational kinetic energy. He would not have linear kinetic energy, all right? And so what we're going to then deal with today is how to just use kinetic energy principles to come up with pretty much the same thing we did using Newton's laws and fibula. All right, but anywho, what we're going to take a look at is if you are linear, then the amount of kinetic energy that you have is, you hopefully know, that's 1/2 mv squared. Hopefully you don't need me to remind that to you. So if it's rotating, then remember, everything that has a formula for linear motion has a corresponding formula for rotational motion. You just change different letters to look like they're Greek letters, all right? So the 1/2 stays the same. The mass then isn't replaced with a Greek letter, it's replaced with the I, that moment of inertia. So there's an I, and then the V's are replaced with omegas, the funny looking W's, and so the rotational equivalent of kinetic energy is 1/2 I omega squared. All right, and if an item is doing both, then, well, you have both. So, what I was saying before, picture a locked bicycle wheel. So somebody jams on the brakes of a bicycle wheel, that thing is skidding. It is moving linearly, it is not rotating. So the kinetic energy is simply 1/2 mv squared. That's easy. If you're riding an exercise bicycle, right? So the bicycle's stationary, it's not moving, but boy, you got that bicycle wheel going nuts. It's going in circles. So if you're riding an exercise bike, stationary, the wheel is rotating, and the amount of kinetic energy inside that wheel is 1/2 I omega squared. Cool. And if you're just riding a bicycle, doing whatever, you just riding a bicycle. I want to ride my bicycle. Someone should write a song. I tell you what. Then the kinetic energy is both. It has 1/2 mv squared, and it has 1/2 I omega squared. Okay, you just push the plus button. It's really that simple. Okay, too easy. So what I'm going to do again is go back to what we did in a previous video that I was alluding to with that guy rolling downhill, that solid cylinder rolling downhill. And the situation was to generate an expression for what the speed of that cylinder would be at the bottom of the hill, but using letters. Okay, we got to get used to doing math with letters, which you already are used to doing math with letters. And they'll just say, simplify an expression. What's the speed of that sucker at the bottom of the hill? What we did was use Newton's laws, which was the F equals ma. I mean, that's easy. And kinematic formulas, specifically, it was 5 EULA because you didn't have the time to get the speed at the bottom of that incline. And if you remember, the velocity at the bottom of that hill was 4/3 GH. All right. So now what I want to show you is how to do the exact same thing, but it's going to be a lot fewer steps because we're going to use energy instead of the Newton's laws and the kinematic formulas. All right, so I've shown you several of these types of things before throughout the school year, how the 5 EULA simplifies down to the kinetic energy formula anyway. But here's another example. All right. So this is the exact same situation that we had a few videos ago. This is a solid cylinder of radius r, mass m. It's rolling down an incline of height h at some angle theta. I mean, who cares? Whatever. Just it's all going to be letters anyway. Again, the key that they'll say is this thing is rolling without slipping. All that means is it's rolling without slipping. So let's generate a formula or an expression for how fast this guy is going at the bottom of the hill. And they'll always say in terms of a whole string of letters. That doesn't mean you have to include all of those letters. Those are just letters that are options for you that you're allowed to include. And whenever it says fundamental constants, it just means you're allowed to use little g in this example, capital G if it's a gravitational interaction, things along those lines. Fundamental constants. All right. So all we're going to do is just use energy. This formula should look very familiar. The sum of the energy at the top is the same as the sum of the energy at the bottom. Well, at the top of that incline, it's just like you, all potential. No kinetic energy at the top, and then I have rho, R-O-T is just what I use. Sometimes I get lazy and just use the letter R, R-K-E for rotational kinetic energy. All right, now, at the bottom, it's like others of you, none potential. But all kinetic energy at the bottom plus the rotational kinetic energy at the bottom. All right, so what I'm going to do is just kill what needs killing. That's 0, and this is after Nagel. All right, so the potential energy at the top is simply mgh at the top, right? Whatever that height is, that's easy. I'm going to set it equal to the kinetic energy at the bottom. That is 1/2 mv at the bottom squared. And to that, I'm going to now add the rotational kinetic energy at the bottom, which is 1/2 I omega squared. All right, now, just to remind you, we were talking about a solid cylinder. The I of a solid cylinder, which you don't have to memorize, but you should be familiar with it by now. It's 1/2 mr squared, okay? This whole problem would stay exactly the same if it had a different shape. The only thing that would change is whatever that fraction is in front, all right? So remember that this strategery will hold true regardless, as long as you're rolling downhill, okay? So what I'm going to do is replace that I with 1/2 mr squared. So this will be mgh at the top is 1/2 mv at the bottom squared plus 1/2. Now, that 1/2 is that 1/2. I am now going to write what is in red, 1/2 mr r squared. So that which is in parentheses is the I, and now I will multiply it by the omega squared. Okay, so it's a half of an mr squared. All right, so this side of the equation doesn't really change. It's mgh at the top. That's going to be the same thing as 1/2 mv at the bottom squared plus. Now I'm just going to distribute that 1/2. It just becomes 1/4 mr squared omega squared. All right. Now, what I want you to remember, and I'm sure you all know this by now, good Lord, we used A as equal to Ralpha. We've used several of those swappertunities. Here we're going to have a swappertuna V, quite literally. B, because you remember that V is equal to rho omega, right? R omega. Well, in this expression, we have an r squared omega squared. Well, r squared omega squared is that's a v squared. So what I'm going to do is literally replace that r squared omega squared with another letter v squared. All right, so this will look like this. It'll be mgh at the top is equal to 1/2 mv at the bottom squared. Now I'm going to add 1/4 m. And again, that r squared omega squared becomes v squared. So v squared. And look at that. Holy shnikes. Well, we can go back to history class now. We can kill the masses. And that dies, and that dies. And what are we left with? We have a g, h, at the top, which I guess I don't need an H with the letter T next to it. That's both repetitive and redundant, but what the heck. I got a half plus a fourth. Fractions are very divisive, but I'm still going to leave them. That's going to be 3/4 of the velocity at the bottom squared. All right? Now, what I'm going to do is just solve for that velocity at the bottom squared. So this will be what? 4/3 gh at the t equals the v at the bottom squared. So the v at the bottom is clearly 4/3 gh. And if you want to put the letter t there for the top, go right ahead. But let's square rootify it. And hopefully you guys remember what I said at the beginning of the video or from a couple videos ago. That's the exact same answer we got when we used Newton's law, F equals ma, and substitute that a, what acceleration we got, into 5-ULA's letter A equation. So it's the same as, I guess I should write as using F equals ma and 5-ULA. Okay, so again, just remember, if it's a different shape rolling downhill, if it's a sphere, I think that was what, 2/5 mr squared. A hollow sphere is a different I shape. If it's a hollow or a solid cylinder, it was 1/2. If it's a hollow cylinder, it's just mr squared. All you're going to do is just change what that is, okay? But anyway, this type of math, doing math with letters, all right? Letters. Please remember that's 90% of what we're doing here. And they are going to start including rotational quantities in our kinetic energy. So all you do is just push the plus button if it's moving linearly and rotationally. If it's only doing one or the other, then don't push the plus button. Just, do whatever it is. All questions are not created equally. They are all created similarly. But shoot, with that, it's the same thing. Oh, yeah, there's the equation I was looking for. That equation was to be at the bottom, 4/3 GH. All right. Anywho, that's about all I got. We're coming up on 15, but hey, miss y'all. Yay, physics.